Okay, so in this example, we're going to take a look at cylindrical capacitors. And you might be wondering what a cylindrical capacitor is. Well, if you could picture a piece of coaxial cable, and only two ends are tied to or only one end is tied to the battery, then you have a cylindrical capacitor. So it is actually something that wouldn't be too difficult to make. Anyways, the cylindrical capacitor, it is a Gaussian, an ideal Gaussian geometry, which is good for us. That kind of sets the tone for the problem. And I've drawn a couple of images. Hopefully you can see the three-dimensional aspect of this image, where this is the central conductor passing down in through the middle of the outer conductor. And the outside edge of the inner conductor is located at a radius of A, and the next edge, the inside edge of the outer conductor, is located at a radius of B. Now, it's quite common to just show the end of the capacitor as though you're trying to look down into a pipe, and so we would just have this image with two circles. Possibly they would, add some thickness to the outer circle, if it happens to be like a thick-walled pipe or something like that. So, just pay attention to the little details like that. But basically, this is what we're looking at. So, in order to solve this problem, we start with our definition for capacitance, which is C is equal to Q over delta V. And we don't know what delta V is, so that means we're going to go to the integral of E dot ds. Remember, this is an ideal Gaussian symmetry, so this is going to be real easy to find the electric field as a function of position. And actually, before I even go any further with that, I just want to point out that when you look at the electric field inside of the capacitor, it's going to go from this outer surface to this inner surface, and it does point somewhat radially, and so the field weakens as you go out. I don't know if you were able to visualize that before, if you gave it any thought, but it is something of this radial pattern, and therefore, we don't have that uniform field. Okay, so finishing this up now, so we have the integral of E dot ds, and we still need E as a function of R, so that means we go to Gauss's law, and Gauss's law is the integral of E dot dA is equal to Q enclosed over epsilon naught. So E is going to be constant everywhere at our Gaussian surface. So everywhere along that line, E will be a constant. And so we can write this as E times the integral of dA, but dA is just going to be the area of the soup can wrapper. And so this becomes 2 pi r times the length of our capacitor. And Q enclosed, we're going to assume that Q is known. There's no reason to have to write this as a charge density, but for right now we're going to assume that the charge is known, and so we just write this as Q over epsilon naught. And so E is equal to Q over 2 pi RL epsilon naught. Now we're going to substitute that into our expression for delta V, and we get delta V is equal to minus the integral of Q over 2 pi R L epsilon naught dr. And all of this is constant except for the r, so we can pull it outside of the integral sign. So we have delta V is equal to minus Q over 2 pi L epsilon naught times the integral. And now let's set up our limits of integration here. We're going to go from A to B, from the inner to the outer. So this is going to be from A to B of dr over r. And so by now you should be familiar with that integral. We get minus q over 2 pi L epsilon naught times the natural log of r evaluated from A to B. And so we can finish writing this as delta V is equal to minus q over 2 pi L epsilon naught times the natural log of B over A. And then we can substitute this into our expression for capacitance. And therefore we get the capacitance is equal to Q over minus Q divided by 2 pi L epsilon naught times the natural log of B over A. So the 2 pi L epsilon naught goes in the numerator. The Q's cancel out. And so we get C is equal to 2 pi L epsilon naught over minus the natural log of B over A. And the only thing we're going to do now to change this up is get rid of the negative sign. And we do that by switching A and B. And so the capacitance is going to be equal to 2 pi L epsilon naught over the natural log of A over B.